Hi everyone, Dr. Burns here. Let's continue our conversation on factors that can affect our reaction rate. We've talked previously in our last lesson about how concentration can affect our reaction rate. And now we're going to continue that discussion on how temperature can affect our reaction rate. So we've discussed previously that the minimum amount of energy necessary to form a product during an effective collision is called the activation energy. And this is the primary factor in the rate of the reaction. If the activation energy is much larger than the average kinetic energy of the molecules, then the reaction will occur slowly. So if the average kinetic energy is small in comparison, so if EA is much larger than the average kinetic energy, then we're going to have a slow reaction because it's going to take longer for those molecules to collide with each other and have effective collisions occur, because remember, an effective collision, first we have to think about the energy that's involved as well as the orientation. Even if they're orientated in a way that would promote the production of product, if there's not enough energy, then we're not going to see the product form. And the energy is going to be determined by how fast they're moving. And we know that how fast a molecule is moving depends on the temperature. So that's where we're going to start seeing that temperature dependence. If the activation energy is much smaller than the average kinetic energy of the molecules, so we can think of maybe the molecules are moving much faster now in comparison to our first one, our activation energy, let's throw an A there, is smaller than the average kinetic energy, then a large fraction of those molecules will be adequately energetic and the reaction will proceed rapidly. So if we're thinking about the temperature dependence, this first scenario would be colder temperatures. And again, that's going to be relative to the actual reaction that's at hand, whether that's what colder means. Okay, but we could think of colder being slower, and our second one being hotter. Hotter meaning faster. Again, that temperature is kind of relative to the specific reaction. And the average kinetic energy of the molecule is determined by the temperature of the system. So we're going to see how changing the temperature is going to then affect the activation energy, or the average kinetic energy, to go along with the activation energy. So this is brought about by the Arrhenius equation. The Arrhenius equation relates the activation energy and the rate constant for many chemical reactions. And that equation is presented here, where the rate constant K is equal to A, E raised to the negative E sub A over RT. Now there's some new terms in here that we have to define, but let's look at the ones that we know already. We know K. K is going to be our rate constant. A is a new term for us. A is going to be something called the frequency factor, and it represents the collision frequency for a given reaction. So if the frequency factor is low, then there's not many collisions happening. If there's not many collisions, then we're not going to have a very fast rate because there's going to be not much product being formed. E sub A, that's our activation energy, we know that one. And our activation energy in these types of problems will have units of kilojoules per mole. R is a constant we've seen before back in General Chemistry 2, capital R. That's going to be our gas constant. Okay, and our gas constant here is going to be 8.314 joules per mole Kelvin. But since our activation energy is typically in kilojoules per mole, we can rewrite this as 0.008 314 kilojoules per mole Kelvin. Just so we already have that in our units of kilojoules, but you can write it either way. Capital T is we're now back to temperature. Remember, capital T is temperature, lowercase t is time. So we'll say that lowercase t is time. Capital T is temperature. We're not using time here currently. So we're not using time here. Okay, and then we've seen this previously, and you may have seen it in your math classes before, but this lowercase e is the base of a natural logarithm. It's how we get rid of natural logs. It's how we cancel out natural logs. So we've seen that a little before in our integrated rate laws, and here we're using it for our Arrhenius equations. So this is the Arrhenius equation where we're relating the activation energy and the rate constant for chemical reactions. Now there is some calculus that's involved with the Arrhenius equation to write it in a form that's a little bit more understandable and can be utilized in multiple different situations. So if we take the natural log of both sides, the Arrhenius equation can be written in ln of k equals the natural log of A minus the activation energy over RT. And we can rearrange that a little bit just to make it look, or give it a linear form. So natural log of k, that's our y. EA over R is our m. 1 over t is our x. And natural log of A is our b. So again, like we saw in our integrated rate laws, we are going to have, it's sometimes easier to have things in a linear form. Again, for the graphical side of this chapter, again, we are not going to be graphing anything and solving anything on the graphical side of chemical kinetics, but the equations that they utilize are a lot easier to utilize in just regular problems. So this is just another form of the Arrhenius equation that we can utilize that sometimes just makes it easier to solve for a specific variable. So let's practice utilizing this equation. Just like with our integrated rate laws, the Arrhenius equation just comes down to an equation that we have and we know the variables and we solve for our unknown. We just have to double check that we have all of our units correct and everything is working out. So the decomposition of N2O5 at 308 Kelvin has a rate constant of 1.35 times 10 to the minus 4, 1 over seconds. The Arrhenius constant for this reaction is 4.79 times 10 to the 13. Calculate the activation energy in kilojoules per mole for this reaction. Now you can utilize either of the two equations that we have here to solve for the activation energy, EA. Okay, so we're solving for EA here. I personally think that using the second version of the equation here is going to be easier because you're not having to worry about solving for an x that's in an exponential like we have here. If you easily understand natural logs and would be able to, use a natural log to cancel out that e, then that's totally fine. But since we already have the equation where that e has been canceled out with natural logs, we might as well just use that one, just for the ease of it, and to ensure that we're not going to make any calculation errors. So let's define our variables. We have k, the rate constant, was given as 1.35. times 10 to the minus 4. EA is what we're looking for. R is our gas constant, which we have as 8.314 joules per mole Kelvin, but since we know we're looking for this in kilojoules, let's rewrite it as 0.008314 kilojoules per mole Kelvin. Okay, again, I just divided that by 1,000 to cancel out joules and get to kilojoules. Then we have T, which is equal to 308 Kelvin. Let's note here that our R has units of Kelvin, which means our temperature also has to be in units of Kelvin. So if you're given a value of temperature in degrees Celsius, you are going to have to convert that using our conversion factor for Kelvin to Celsius. And finally, we have our variable A, which is the frequency factor. So or also called the Arrhenius constant in this problem. Books call it both or one or the other. It's all the same. The Arrhenius constant, the frequency factor, it's all the same. And that is 4.79 times 10 to the 13 1/seconds. Okay, so we've double checked our units. Everything is in the proper units. Let's throw a unit on that K. So now we can plug everything in and solve. So we have natural log of K, 1.35 times 10 to the minus 4 is equal to negative EA, which is what we're looking for, over R, so 0.008314, times 1 over the temperature, 308 Kelvin, plus the natural log of A, so natural log of 4.79 times 10 to the 13. So let's grab our calculator so we can work on this problem together. Okay, so let's start by simplifying. We have our natural logs that we can solve for, so natural log of 1.35 times 10 to the minus 4. We get negative 8.9102 is equal to negative EA over, let's do 0.008314 times our temperature, 308. Simplify that for our math, 2.5607, plus the natural log of A, natural log of 4.79 times 10 to the 13. We get 31.500. Okay, so now we'll simplify to get EA on one side. So we'll take that negative 8.9102 and we'll subtract off 31.5. So we get negative 40.4102 is equal to negative EA over 2.56. Since we have a negative on both sides, we know they cancel each other out, so we'll make both of those positive. And then we'll multiply both sides by 2.56. And we get an EA that's equal to 103.47, and that would be kilojoules per mole coming from our R constant. This has 3 significant figures in the problem, so we're going to call this 103 kilojoules per mole is our activation energy. So that's as much energy that the molecules need to have in order to have an effective collision and form product when they collide. Now there is another form of the Arrhenius equation that we can utilize, and this is specifically when we're comparing the rate constants at 2 different temperatures. So we can see how the rate constant is affected if we were to change the temperature, because we know that the rate constant is going to change if we change the temperature. If we're increasing the temperature, the reaction is going to happen faster. If we decrease the temperature, the reaction is going to happen slower. So a 2-point form of the Arrhenius equation can be written similar to the one we saw before, where we have natural log of our K values, but now we're putting in, we have to look at the 2 different rate constants. As well as the 2 different temperatures. Since the frequency factor isn't going to change, that's going to be specific for the reaction itself. It doesn't depend on the temperature. That term from our previous equation is no longer there because A of one and A of the other are the same, so they cancel each other out. So, if the rate constants at two different temperatures are known, it is possible to calculate the activation energy. Okay, we can do that. As well as if the activation energy and the rate constant at one temperature is known, it's possible to determine the rate constant at any other temperature to see how that rate constant would be affected. So let's practice using this in a problem. The rate constant K for a certain reaction is measured at two different temperatures. So we have K right here and the two different temperatures right here. Assuming the rate constant obeys the Arrhenius equation, calculate the activation energy for this reaction. So the first thing that we're going to have to do is convert our temperatures because our Arrhenius equation still has an R in it. We still have that gas constant present, and that has units of Kelvin. So we have to convert our temperatures to Kelvin first. So let's take 85 and add 273.15 to that to get 358.15 Kelvin, as well as 139. And we get 412. Okay, we have to do that. We make sure we do that. Now we want to find EA from this. So we know our rate constants, we know our temperatures in Kelvin, we know R, that's a constant as well. Let's do 0.08314 kilojoules per mole Kelvin. Okay. So now all we have to do is plug in and solve. So we have our natural log of K1, let's call this first one 1 and the second one 2. So K1 is 6.1 times 10 to the 10, and K2 is 3.7 times 10 to the 11. That's going to equal EA, which we're solving over R, which is 0.008314. And we're going to multiply that by the difference in the temperatures. Now, oftentimes I see students plugging in the wrong values for T1 and T2. So just make sure you're plugging it in the correct value in the correct space, because that is going to affect the value itself. So we have 1 over T2, so T2 comes first, so that's that 412.15, minus 1 over T1, which is 358.15. Okay, so let's simplify. Well, we know our natural logs, so again, as I said in our previous lessons, make sure you're plugging in the ratio correctly. You could do that one of two ways. You could do 6.1 times 10 to the 10 divided by 3.7 times 10 to the 11, and then take the natural log of that answer. Or you could do natural log and utilize your parentheses correctly, do 6.1 times 10 to the 10 divided by 3.7 times 10 to the 11, close parentheses. As long as you make sure that both of those values are in the parentheses, it'll do the natural log of both of them, giving you the same answer. You could do it either way. Okay, so we get negative 1.802 on this side, EA over 0.008314, and then we do 1, let's use our parentheses wisely, 1 divided by 412.15 minus 1 divided by 358.15, and that gives us a negative 0.000365. Now again, it is very important that you put in the correct temperatures in the correct spots, and that's because this negative and that negative will end up canceling. And if you put them in the wrong position, you they would not be negative. There wouldn't be the negative on the temperature. And then you would have a negative activation energy, which you can't have. So just make sure you're plugging everything in correctly. So we're going to take that negative 1.802 and divide it by that negative 0.000365 to get 4,936.99 is equal to EA over 0.008314. And we can solve for EA by multiplying both sides by that R. So we'll multiply by 0.008314. And we get activation energy of 4.1.046 kilojoules per mole. Let's see, we have 2 sig figs in this answer, so 41 kilojoules per mole for our activation energy. So that's utilizing now both versions of the Arrhenius equation. If we're comparing two reactions, or one reaction at two different temperatures, we want to use this 2-point form of the Arrhenius equation. If you only have one temperature and you want to find either the activation energy or the rate constant, okay, then you would use the first form of the Arrhenius equation. Both are provided to you on exams in your test-taking resources. So moving forward, we're going to start discussing reaction mechanisms. So we've talked about how reactions happen. We've talked about the rate at which they happen. We've talked about the effects that can affect that rate and the reaction from happening overall. And now we want to talk about the mechanism that is happening when our molecules are reacting. So a balanced chemical equation does not indicate how a reaction actually takes place. The sequence of steps that sum to give the overall reaction is called a reaction mechanism. So typically what we see up until now is a reaction that's balanced in some way to be A plus 2B goes to product D. Okay, we see this all the time. But what we don't know is, well, did that actually happen in one step? Did it happen in 2 steps? Did it happen in 3 steps? How did that reaction actually come about? Did those two molecules just need to bump into each other and form the product, or did we have to make any sort of intermediate product and then do another reaction with that? Which is typically how most reactions happen. We have some sort of intermediate step. In this reaction, C is our intermediate. Okay, we combined A and B and it created C, but then C combined with B and created D. So we get a total reaction of A and 2B because we used B twice, and we created product D, which is the intended product of that reaction. So chemical species that appear in the reaction mechanism, but not in the overall chemical equation, those are called intermediates. So the actual steps that we have to use to achieve the overall reaction, this is called the reaction mechanism. And any piece of that reaction mechanism that is not a product or a reactant in our balanced overall reaction is considered an intermediate. So in this case, N2O2 is the intermediate. It's created in our first step, and then it's utilized as a reactant in our second step, so it essentially cancels itself out. If you think back to Hess's law, when we have two reactions and the same compound is on both sides of the arrow, it cancels itself out, and then we can add those two reactions together to get 2NO, 1O2, and 2NO2. So very similar to how we can think about Hess's law from our previous lessons. Each step in a reaction mechanism represents an elementary reaction. So this is something that is simplified, okay? I think elementary I think, simplified. And that is a reaction that occurs in a single collision of the reactant molecules. So those reactant molecules just have to collide with each other first to create their product, whether that's the product of the overall reaction or an intermediate. The molecularity, which is a new fun word to say, molecularity, okay, of an elementary reaction. So for each step that we see, for each elementary reaction in our reaction mechanism, is essentially the number of reactant molecules involved in the collision. So if we have something that is unimolecular, uni meaning one, then we have one reactant molecule. So A going to product would be a unimolecular reaction. Then we have bimolecular, bi meaning two, and that's two reactant molecules that are coming together to form the product, whether that's two different molecules or two of the same molecules. We finally have termolecular, where ter means three, which is three reactant molecules. So you can have A plus B plus C going to product. You can also have A plus B going to product, and a bunch of other variations of that. But you have three molecules that are participating in that elementary reaction. So if we look back at our old example here, this first step would be bimolecular because it has two reactants, and the second step would be bimolecular as well because it has two reactants. Even though one of those is an intermediate, since each elementary step can have a different molecularity, we can have an intermediate that contributes to that molecularity. Now, how does this relate to the rate? If we're going to have multiple steps, how do we think about that in terms of the rate overall? Right? If we know just the balanced reaction, how do we know that there's multiple steps that go on? How do we know which of those steps is going to determine the rate? Well, we have something called the rate determining step. In a reaction mechanism consisting of more than one, there's a typo there, more than one elementary step, the rate law for the overall process is given by the rate determining step. So if we know the rate law, then we know the rate determining step. And you can think about it kind of generally. If the rate is going to be determined by one step, and that's going to be the slowest step possible. Okay, that rate determining step is going to be the slowest one because it's determining the rate of the entire reaction. It's the one that bottlenecks the other reactions. Yes, you can have one that goes fast, but if that second step is dependent on the product of the first step, then the rate is going to be determined by the first step, and that's what's going to determine our rate law. So the rate determining step is always the slowest step in the sequence, and a proposed mechanism must satisfy two requirements. The sum of the elementary reactions must be the overall balanced equation for the reaction, and the rate determining step must have the same rate law as that determined from the experimental data. So let's look at what that actually means. So let's look at the decomposition of hydrogen peroxide. We have two steps. Hydrogen peroxide reacts with iodide ions, so this reaction can be facilitated in a two-step process using iodide. And what's going to happen is we're going to form water and iodine oxide, that iodine oxide is going to be our intermediate, right? Because it has nothing to do with the decomposition of hydrogen peroxide. Okay, if we looked at that balanced reaction down here, the overall reaction, there's no iodine there. Okay, so we have an intermediate in iodine oxide, but that iodine oxide then reacts with any excess H2O2, any excess hydrogen peroxide, to create even more water as well as oxygen gas and iodide ions. So we see we have two intermediates here that end up canceling each other out because they're intermediates. So experimentally, the rate law was determined to be rate is equal to K1 times the hydrogen peroxide concentration times the iodine ion concentration. And this was determined experimentally. And that's what we learned in our previous lesson, how to determine that using the method of initial rates. So we now have to look back. I'm going to erase some of this so we can see it clearly. If we want to determine the rate determining step, we have to look at the rate law that was determined experimentally and say, okay, which one of these steps has H2O2 as a reactant and I- as a reactant? Well, our first step has H2O2 as a reactant and I- as a reactant. And the second one has H2O2 but does not have the I-. It has IO-, but that's not what the rate law was determined to be. So that means that because the rate law has H2O2 and I- in it, the rate determining step is step 1, which was also noted by the fact that it has the slow notation, because the slower of the two or more reactions is going to be the rate determining step. Let's practice this a little bit more. So the gas-based decomposition of nitrous oxide, N2O, is believed to occur in 2 steps. Experimentally, the rate law was found to be rate is equal to K times the concentration of N2O. We have 3 questions that we need to answer. First, write the equation for the overall reaction. Identify the intermediate or intermediates. And then identify the rate determining step. So our overall reaction is going to be similar to how we worked with Hess's law. Okay, so we're going to add up both equations. So we're going to have N2O plus N2O plus O goes to N2 plus N2 plus O plus O2. I just added those both up. We can now start to combine. So we have 2 N2Os plus an oxygen goes to 2N2 plus an oxygen plus an O2. Okay, now we can look at what cancels. Well, oxygen and oxygen are on both sides, so they cancel each other out. So that simplifies our reaction to be 2N2O goes to 2N2 plus O2. Whatever was canceled is then our intermediate, so the intermediate is O. Finally, we want to identify the rate determining step. Well, the rate determining step has to have the same rate law as the one determined experimentally. The rate law was determined experimentally to be rate is equal to K times the concentration of N2O. So we need to look for which step has only N2O as its reactant. Well, step 2 has N2O and oxygen, which was our intermediate, so that's a no, meaning step 1 only has N2O as a reactant, leaving this as the rate determining step. Okay, so we're just relating our rate law to our multi-step process, to our elementary reactions. Finally, we want to discuss catalysis. In catalysis, a catalyst is a substance that increases the rate of a chemical reaction without itself being consumed. So again, we have our reaction of hydrogen peroxide being facilitated by I- or iodide ions. Here we can see that we started the reaction with iodide and we ended the reaction with iodide as well. And the only reason it doesn't show up in the overall reaction is because it cancels itself out. But it was not consumed, right? It was utilized to create our product in our first reaction, but because it was then a product of the second reaction, we got out just as much as we gave in. So it was never actually consumed in the reaction, because for each molecule of iodine ion that we used, we got out another molecule. So we could see iodide ion as the catalyst because it is not being consumed and it is thus increasing the rate of the reaction overall. A catalyst will speed up a reaction by providing a set of elementary steps with more favorable kinetics than those that exist in this absence. Specifically, the catalyst will speed up the reaction by lowering the activation energy. So if our activation energy is much lower, it's more favorable to follow that reaction path. Imagine if you were hiking through the mountains and you had to get to a specific spot. You have two choices, one that has a lower hill or one that goes over the top of the mountain. You're going to choose the one that goes over the lower hill because it's going to exert less energy. Less energy is more favorable. So let's look at how that looks in our reaction pathways. We've looked at reaction pathways a little bit before when we talked about activation energy. We looked specifically at this first one. Okay, we said we start with our reactants, the molecules start to move closer together, they reach the top where they reach that transition state, and then the bonds change, we form our products, and the molecules start to move further apart. Okay, so we have an activation energy, it's a pretty large hill. This would be an uncatalyzed reaction. If we were to add a catalyst to the reaction, okay, then we start in our reactants, but the hill that we have to go over is going to be much smaller in comparison. So look at that. It's almost like half of the activation energy of the uncatalyzed version. This is going to be significantly more favorable for a reaction pathway rather than the first one because it utilizes less energy, but the outcome is still the same. So if we can use less energy, we could then use that energy elsewhere and maybe create more product. So we head over our transition state and again go to our products. So the rate of the catalyzed reaction is much faster than the rate of the uncatalyzed reaction. We have a couple different types of catalysts that can be utilized in a chemical reaction. First is a heterogeneous catalyst, and that's the reactants and the catalysts are in different phases. So we have maybe a solid and a liquid or a liquid and a gas. Okay, they're in different phases. Homogeneous is when the reactants and the catalysts are dispersed in a single phase. Typically, this happens with liquids. And finally, one that we all may be more familiar with is enzymes. Enzymes are biological catalysts. We have these in our body that help us digest food and everything like that. Essentially what they do is they mimic the substrates that would bind and allow that substrate to break down into its products much faster. So we need enzymes in our body in order to break down so many different things like proteins, fats, and everything like that. So they end up changing that reaction rate or the rate at which we're forming the products and breaking down whatever we need to.